Hello, in this video we'll be working through Unit 4 homework problems 44 through 48, and these problems deal with optimization. Number 44, we have a rectangular box with a square bottom and a closed top. So let me go ahead and draw the box. It's got a square bottom. Mine looks like a cube, but it doesn't necessarily have to be a cube. Closed top means we have a top and a bottom, and it's going to be made from two materials. The material for the side is $1.50 per square foot. So we've got the side of the box, and the cost there is $1.50 per square foot. The material for the bottom costs $3 per square foot. And it's a little unclear in this problem, but let's assume that the bottom and the top of the box are made from the same material. So the bottom and the top are going to cost $3 per square foot. If you're willing to spend $15 on the box, so that's total, what is the largest volume it can contain? Largest volume. We want to find the maximum volume. So we're going to need to write a volume equation. Think about what are the variables in this problem. The bottom of the box is square. So if we call this side x, then this side also has length x. But the height of the box could be anything, not anything, but it doesn't have to be x. So we've got two variables here, x and y. We're trying to maximize the volume. That means we need to write a volume equation and then find the absolute maximum of that equation. So volume equals length times width times height, or x squared times y. Now we've got one too many variables here, so we're going to use a secondary equation. And we can use our cost information to do that. Now the cost is going to be defined in terms of the surface area of our rectangular box. So the surface area of our box is the top and the bottom, and the top and the bottom have the same area, so 2 times the area of the bottom is x squared. So 2x squared is going to give us the area of the top and the bottom, plus, and the area of the sides. We've got 4 sides, and each one has an area of x times y. And then our cost, total cost, $15, and that's going to be the 2x squared, the area of the top and the bottom, times 3. So the 2x squared times 3 is 6x squared. And then the cost for the sides is $1.50 per square foot, and the amount of square feet is 4xy. So we're going to multiply 4xy by $1.50, and that's going to give us 6xy. So from this equation, we've got an equation here with two variables. We can solve for y and then substitute that into our volume equation to eliminate the extra variable. So if I'm solving this for y, I get 15 minus 6x squared over 6x equals y. So we're going to substitute that into our volume equation, which is going to give us volume equals x squared times 15 minus 6x squared over 6x. And then we can simplify this. X squared over 6x is just going to be x over 6. So 1 over 6 times x times 15 minus 6x squared. I'm going to go ahead and distribute the x. So I have volume equals 1 over 6 times 15x minus 6x cubed. Now that I have my volume equation written in terms of a single variable, I'm going to take the derivative. So we're going to take the derivative of volume with respect to x. So dv dx equals 1 over 6 times 15 minus 18x squared. Now to figure out where I have a maximum volume, I want to know, where does this derivative equal 0? I want to get that critical value or values. This is going to equal 0 when 15 minus 18x squared equals 0, or when 15 equals 18x squared, or when x squared equals 15 over 18, which reduces to 5 over 6. So x equals plus or minus square root of 5 over 6, but x can't be negative in this problem, so x equals the square root of 5 over 6. Now that's the only critical value we found, so hopefully that is a maximum. We can do either a first derivative test or a second derivative test to check that that is in fact a maximum. If I put square root of 5 over 6 on a number line, then check the sign of v prime around that value, so we can use 1 as a value larger than the square root of 5 over 6. And putting 1 into my derivative equation is going to give me a negative derivative. If I use 0 in my derivative equation, I get a positive. So v is increasing to that point and then decreasing. So it is in fact a relative maximum, and that is our absolute maximum. We're trying to find the largest volume. So we need the y coordinate. We need to know what is the volume when x is square root of 5 over 6. So we go back to our volume equation. We can use this volume equation, but this volume equation has a y in it. So if we're going to use this volume equation, we have to solve for y. Or we can go to this volume equation, or here, let's use our simplified version right here. So this volume equation, or this one also, is written in terms of just x, to figure out the volume when x is square root of 5 over 6. And this is a calculator active question. So using our calculator, we get volume equals 1.521 cubic feet. Number 45, the sum of two non-negative numbers is 20. Find the numbers if the sum of their squares is as large as possible. So we want to maximize the sum of the squares of two non-negative numbers. So we need to, this one, it doesn't really make sense to draw a picture, so we can skip that step. But we want the sum to be as large as possible, so maximize the sum of their squares, the sum of their squares. So if our two numbers are x and y, then the sum of their squares would be x squared plus y squared. And we need to call that something, so I'm just going to call it the sum. We also know that the sum of the two numbers is 20. We also know that the sum of the two numbers is 20. So we know that x plus y equals 20. So we can solve for y equals 20 minus x, and then substitute that in for y in my primary equation. So then I have s equals x squared plus 20 minus x squared. And we can simplify this some more, or we can just go ahead and take the derivative now since we have it written in terms of a single variable. So s prime is 2x plus 2 times 20 minus x times the derivative of 20 minus x, which is negative 1. And simplifying that, we get 2x minus 40 plus x, or 3x minus 40. So that's the derivative of the sum of the squares. And to find the absolute maximum, we're going to use a first derivative test. Our critical value, if we're setting this equal to 0, we get 40 over 3. And in terms of possible endpoints, we are told that the numbers are non-negative, so the smallest they can possibly be is 0. And their sum is 20, so the largest each one could possibly be is 20. Now we're going to pick test points. So 40 divided by 3 is more than 1. So we can use 1 as a test point. Let's put that into our derivative. 3 times 1 minus 40, that is negative. And then we can use 19 as a test point over here. So 3 times 19 is 57, minus 40 is positive. Okay, so S prime is positive, which tells me that the sum changes from decreasing to increasing. So this is a relative minimum. We're trying to find a maximum. So it's going to be one of our endpoint values that we're looking for. So let's find S of 0 and S of 20 and see which one gives us the larger sum. Well, our equation for S is x squared plus y squared. So we can solve for y, or we can use the version of our equation that is written only in terms of x. And if we do that, then when x is 0, the sum is 0 plus 20 squared, or 400. When S is 20, we'd have 400 plus, and then 20 minus 20 squared is 0. So either way, we get 400. So that means our x is either 0 or it's 20. But if x is 0, then, and we go back to this equation here, x plus y is 20, then we know that y is 20, and vice versa. If x is 20, then y is 0. So the two numbers are 0 and 20. The two numbers that will maximize the sum of squares would be 0 and 20. Now, to minimize the sum of the squares, we would use this relative min value. If we check S of 40 over 3, I'd have 40 over 3 squared plus 20 minus 40 over 3 squared. So that's 1600 over 9 plus 20 I can think of as 60 over 3. So 60 over 3 minus 40 over 3 is 20 over 3. And 20 over 3 squared is 400 over 9. So we get 2000 over 9, which is a little more than 200. So it is a smaller value than our endpoints give us. Okay, so we have, the question is asking us to find the numbers. So for part A, the numbers are 0 and 20. And for part B, the numbers are 40 over 3, and then we have to find y. Remember, these sum to 20. We've got x plus y equals 20. So 40 over 3 plus 20 over 3 is going to equal 20. So 40 over 3 and 20 over 3 would be our two numbers. For part C, we want one number plus the square root of the other to be as large as possible. So we're trying to maximize x plus the square root of y. We still have the fact that x plus y equals 20. So y equals 20 minus x. And now our equation, the sum, is x plus the square root of 20 minus x. We want to maximize that sum, so we're going to find the derivative. S prime equals 1 plus the derivative of square root of 20 minus x. So that's 1 over 2 times the square root of 20 minus x times the derivative of 20 minus x, which is negative 1. Now we want to know where this has a maximum, and then for part D, we want to know where this has a minimum. So let's try and find our critical value. We've got 1 minus 1 over 2 times the square root of 20 minus x equals 0. So I can add the second term over to the other side. I get 1 equals 1 over 2 times the square root of 20 minus x, multiply both sides by 2. I get 2 equals 1 over square root of 20 minus x, take the reciprocal of both sides, and then square both sides. I get 1/4 equals 20 minus x, and then solving for x, we get x equals 20 minus 1/4. So x equals 19 3/4, or 20 over 4 or 20 we can think of as 80 over 4. Minus 1 is 79 over 4. And then when x is 79 over 4, y equals, looking over here, y equals 20 minus that number, which would just be 1/4. So remember, these two add to 20. So our critical value, we only got one critical value at 79 over 4. And again, we have endpoints at 0 and 20. So let's try a test point. When x is 1, let's go back to our derivative equation. So we can use, I guess, this equation right here. If x is 1, we get 1 plus -1 over 2 times the square root of 19. 1 over 2 times the square root of 19, that number is a lot smaller than 1. So even though it's negative, the entire sum will be positive. But 79 over 4, remember that came from here, it's 20 minus 1/4, so that's 19 3/4. We need a number that's bigger than 19 3/4. Okay, so I'm going to use my calculator and I'm just going to check at like 19.9. And that is negative. Okay, so that tells me that S is increasing until we hit that critical point and then decreasing after that. So we have a relative max here. And it has to be the absolute max because there are no other turning points. So to make this sum as large as possible, the numbers are going to have to be 79 over 4 and 1/4. Now to make this sum as small as possible, we're looking at one of these endpoints. So we need the sum at 0 and the sum at 20. So we go back to our original equation, which is right here. If x is 0, y is 20, which we can get from here. So when x is 0, I would have 0 plus the square root of 20. And when x is 20, I would have 20 plus the square root of 0, which is 20. The square root of 20 is smaller than 20, so I want my sum to be the square root of 20. And that happens when x is 0 and y is 20. So the first number is 0. The one we're taking the square root of is the 20. Number 46. A farmer wants to start raising cows, horses, goats, and sheep and desires to have a rectangular pasture for the animals to graze in. However, no two different kinds of animals can graze together. In order to minimize the amount of fencing she will need, she's decided to enclose a large rectangular area and then divide it into 4 equally sized pens or grazing areas. She's decided to purchase 7,500 feet of fencing. What is the maximum possible area that each of the 4 pens will enclose? So we're trying to maximize the area of each pen. So let's draw a sketch. We have a rectangular field and we want to divide that into 4 equal rectangles. So we want to find the area of each one of these. So I'm going to let this short side be x and this longer side equal y. And then the area for each small pen is x times y. We also know that she has 7,500 feet of fencing. So the total perimeter, well, also including the inside, we've got 1, 2, 3, 4, 5, 6 of these x's plus 1, 2, 3, 4, 5, 6 of the y's. So 6x plus 6y will total 7,500. And we can use this secondary equation, solve it for y. We get y equals 7,500 minus 6x all over 6. And now I can substitute that in for y in my area equation. So the area is x times 7,500 minus 6x over 6. Now we have an equation written in terms of a single variable. So this is what I'm trying to maximize, this area equation. If I take the derivative now, I have to use product rule. So I'm going to go ahead and simplify this a little bit. I'm going to bring out the 1/6, and I'm going to distribute the x. So distribute the x, but then factor out the 1/6. So it's 1/6 times 7,500x minus 6x squared. The derivative of a with respect to x is 1/6 times 7,500 minus 12x. We want to know where is that derivative equal to 0. Well, that's going to be wherever 7,500 minus 12x is 0. So 7,500 equals 12x. So x equals 7,500 over 12, or 625. Now we can solve for y using this equation here. So 7,500 minus 6 times 625 all over 6 is also equal to 625. Now we should check to make sure that that really is a maximum. Just because it's a critical value doesn't automatically make it a maximum. So 625. We have 7,500 feet of fencing. So we can figure out like the minimum and maximum possible values for x. Well, the minimum would be 0. And the maximum, you might say 7,500. I mean, I could put that, but it's going to be a lot less than that because remember we have 6 x's that are going towards the fencing. So it's really 7,500 over 6 would be my maximum, or 1,250. And then test points for our derivative equation. If we let x equal 1, 7,500 minus 12 is positive times 1/6 is positive. If I let x equal 1,000, 7,500 minus 12,000 is going to be negative. So we do have a maximum here, and it's not only a relative max but also an absolute max. So this will be the dimensions of the pen that maximizes the area, and the area is x times y, or in this case 390,625, and the units there would be feet squared. 47. Two vertical towers of heights 60 feet and 80 feet stand on level ground with their bases 100 feet apart. So 60-foot tower, 80-foot tower, and the distance between them 100. A cable is stretched from the top of one pole to some point on the ground between the poles and then to the top of the other pole. What is the minimum possible length of cable required? So this plus this. We'll let this distance equal x, the distance from the 60-foot tower to the point on the ground where the cable is attached. And then that means in this other triangle, this length is 100 minus x. We know the other legs of the triangles, it's 60 and 80. And from that, we can get the hypotenuse of each one of these triangles since they are right triangles. So the length of the cable is going to be the square root of 60 squared plus x squared plus the square root of 80 squared plus 100 minus x squared. So that's the sum of the hypotenuse of each one of the right triangles. We want to minimize this length. So we want to find the absolute minimum for this equation. We're going to take our derivative, and we're going to use chain rule here. So it's the square root of stuff. The derivative is 1 over 2 times the square root of the stuff, so x squared, times the derivative of the inside, the 2x, plus, and then over here, same thing, we need chain rule. So it's going to be 1 over 2 times the square root, 80 plus 100 minus x squared, times the derivative of the inside. Derivative of the inside is 2 times 100 minus x times the derivative of 100 minus x, which is negative 1. So put the negative here. So we've got 2's canceling here, which didn't help a whole lot, but it's a little bit simpler. So now we have x over the square root of 60 squared plus x squared, and then minus 100 minus x over the square root of 80 squared plus 100 minus x squared. So we want to know, where does our derivative equal 0? Now, if I were doing this without a calculator, I would get a common denominator, set the numerator equal to 0, try and find my critical values that way. But this is a calculator active problem. So I'm going to find my critical value by graphing my derivative equation and seeing where it's equal to 0. Now, I will point out that since we are using a calculator, we could just graph the original equation and see where it has a minimum value. I mean, that's the easiest way. If I were actually trying to solve this problem just on my own, that's what I would do. But it does say justify your answer using calculus. So we're going to have to find our critical value and show that we have an absolute minimum. Okay, so I graphed my derivative equation and I'm seeing that it passes through the x-axis at an x value of 42.857. And we know x has to be somewhere between 0 and 100. So I can choose a test point. Let's just choose 1 for x. And I get 1 over the square root of 60 squared plus 1, so 3601, minus 100 minus 1, so 99 over the square root of 80 squared plus 99 squared, and that is negative. If I use 99, I get 99 over the square root of 60 squared plus 99 squared, minus 1 over the square root of 80 squared plus 1, and that is positive. So our length is changing from decreasing to increasing. That means we have a relative minimum at 42.857, and it also must be an absolute minimum since it is the only turning point there. We are trying to minimize the length of the cable. So we know this is our solution. And now to answer the question, we have to find the length of the cable. So we go back to our original equation here and we substitute in our x value, 42.857, and we get a length of 172.047 feet. And the final question, number 48, a company is designing propane tanks that are cylindrical with hemispherical ends. Assume the company wants tanks that will hold 1,000 cubic meters of gas, so that's total volume, and that the ends are more expensive to make, costing $5 per square meter. So the spherical part here, $5 per square meter, while the cylindrical barrel between the ends is only $2 per square meter. So this part here, $2 per square meter. Use calculus to determine the minimum cost to construct such a tank. We're trying to minimize cost, so we need a cost equation, and the cost is determined by the surface area. So let's figure out what the surface area of this thing is. The lateral surface area for the cylindrical part in the middle is going to be 2 pi r, if r is the radius of the cylinder here, times h, where h is the height of the cylinder, plus, and then we need the surface area of the two hemispheres. So if we put the two hemispheres together, we get an entire sphere, and the surface area for a sphere, 4 pi r squared. Now the cost for the part that's 2 pi r h is $2 per square meter. So we multiply that by 2 and we get 4 pi r h. Plus, and then it's $5 times the 4 pi r squared. So 20 pi r squared. That's our cost equation. We have variables r and h, so we want to try and eliminate one of those if we can. And to do that, we're going to use the fact that the total volume will be 1,000. So the volume of this thing would be the volume of the sphere, which is 4/3 pi r cubed, plus the volume of the cylinder, which is pi r squared h. That's going to equal 1,000. So now we can solve this for h. H equals 1,000 minus the 4/3 pi r cubed over pi r squared. And we can now substitute that in for the h in our cost equation. So cost is 4 pi r times 1,000 minus 4/3 pi r cubed over pi r squared plus 20 pi r squared. Now we have an equation in terms of r. We want to minimize this cost equation, so we want to find the absolute minimum. We can simplify a little bit. The pi here cancels with the pi here. One of the r's here cancels with one of the r's here, just leaving an r. And now if I distribute the 4, I'm going to get 4,000 minus 16/3 pi r cubed, and that's all over r, or I can divide each one by r, like so, plus the 20 pi r squared. If I keep simplifying, this is 4,000 times 1 over r minus, now this r cancels with one of these r's and leaves an r squared, so 16/3 pi r squared plus 20 pi r squared. Now these are like terms that I can combine, so I'm still simplifying. My cost equation is 4,000 times 1 over r, 44/3 pi r squared. So then we can take our derivative. So the derivative of 1 over r is negative 1 over r squared. So now I have negative 4,000 over r squared plus, and the derivative here, we're using power rules, so the 2 is going to come down, so I'll have 88/3 pi r. Now if we're solving without a calculator, I would want to get a common denominator, so I would multiply the second term by r squared over r squared and write this as one fraction. But this is a calculator active question, so we can get our critical value using the calculator. And that derivative is equal to 0 when r is about 3.514. So once we have r, we're looking for the minimum cost. So once we have r, we can go back to our cost equation here, and we get our cost to equal $1,707.27.